In this video, we're going to continue talking about optimization, and this time we're going to focus on some examples involving open-top containers, or containers that don't have a lid. So let's start off with this example. An open-top box is going to be made by cutting congruent squares of side length x out from the corners. And we're going to start off with an 8.5 by 11 inch sheet of material. You can actually do this on your own and grab a piece of paper that measures 8.5 by 11 and cut out some squares from the corners to really feel how these dimensions are coming in. So we're going to be cutting out squares from the corners and then folding up the resulting sides, and that will give us like a shoebox type figure without a lid. So we want to maximize the volume, find out what's the most amount of space that we can hold in that open top box by cutting out squares from the corners, and then we'll find the resulting volume. So we know we want to work with the volume formula of a prism or a rectangular solid. So the volume is width times length times height. Well, how do we get those dimensions? Well, if I'm cutting out a length here measuring x and a length over here measuring x, then I am taking away two x's from my width and from my length. Well, my width is 8.5, so if I do 8.5 minus 2x, that would be my resulting width right here. And if I take my length, which is 11 inches, and take away two x's, then I get my resulting length right here, which would be whatever 11 minus 2x is. And then if we bend up those resulting tabs, then we can find that the height of our box is really our x value. So we got our 3 dimensions. We can substitute that back into our volume formula and distribute everything. Simplify and get this cubic equation here. I know I want to maximize my volume, so I'm going to find zeros of the derivative. So I can derive this volume formula just using the power rule and get this resulting quadratic. To solve a quadratic, a lot of times we can factor to solve it, but sometimes if we're using decimals, it might just be easier to plug it straight into the quadratic formula, make it a little bit easier and quicker. So plugging A, B, and C terms into the quadratic formula, I get 2 answers that result. And now let's think about which of these answers are actually possible. If I go back up here and analyze my width, if I find the zeros of my width, what would make this a zero width? What x value could I plug in? Well, if I plug in 4.25 and double that, I get 8.5. And if I do 8.5 minus 8.5, then I get a 0 width. I don't want to make a box with a 0 width. So I can't plug in a value that's any greater than 4.25. I also can't plug in values that are negative because we can't have a negative length. So we can think about a domain that we want to work with. We want to plug in values that are in between 0 and 4.25. Those would give us some realistic values that will actually make a box. So going back to our answers or solutions of that quadratic, 4.9 is outside of this domain. It's too big. If I was to plug in 4.9 and try and find my width, I would get a negative width, and that's not realistic. So we'll ignore that solution and just focus on 1.585. If I use that for my square's length and cut out squares with those lengths, then I get a width that is 5.33 approximately inches, and a length that is about 7.83 inches, and a height that was my x value, 1.585 inches. And the resulting volume from those dimensions would give me a box with a volume approximately 41.733 cubic inches. So that's the biggest volume that I could get by cutting squares out of my material. Let's try another example. This time we're going to imagine that we are in a group of engineers designing an aquarium. So an aquarium is not going to have a lid, at least using the material that we use for the sides and the bottom. It's going to have a square bottom, so that's going to be specific, and an open top. and we know that we want our aquarium to hold a volume of 256 cubic feet of water. What dimensions should we use to create an aquarium with the least amount of glass? So we want to minimize our material, we want to minimize our surface area, which would be the material being used to compose this box or aquarium. But I also want to involve volume. So I have two equations that I'm going to be using: volume and surface area. So if I unfold this open top aquarium, I have a square base and four sides that I could then bend up to make this aquarium. So these are our sheets of glass right here. This would be the surface area that we want to use. So let's think about what the surface area of this material is. We know we have a square bottom. So I have an x by x base. So that would be x squared for that area. But then for the sides, we have a height of y and a length of x. So the area of these four sides would be x times y. So we have 4xy's. So the full surface area would be x squared plus 4xy. The volume of this shape would be x times y, or x squared times y, width times length times height. And we know we want our volume to be equal to 256 cubic feet. So if I set my volume formula equal to 256, and I look at my surface area formula, I could then start to think about what I need to do. I want to minimize this formula. And whenever we maximize or minimize or optimize, we tend to want to get just one variable. So we want to somehow substitute this y with something that's in terms of x. So if I go back over to here, in my volume formula, I can solve for y. Just divide both sides by x squared, or multiply by x to the negative 2. And then I can substitute that for y over in this formula. So now I have an surface area formula all in terms of x. And I can begin to derive or minimize these dimensions. So I want to find zeros of the derivative. That's how I find maximums and minimums. So if I derive this formula, I get 2x minus 1024 times x to the negative 2. We could then factor and find zeros. So if I factor out a 2x and then solve the insides here, well, 1 0 out here is just going to be 0. But I can set this equation equal to 0 and solve. So we're just trying to find a cube root of 512. And that would be 8. So we got zeros happening at 0 and 8. Well, I don't want to plug in a dimension of 0 because that would not give me an aquarium. So we'll ignore that solution and just focus on 8. So if x is 8, then that means the width is 8 and the length is 8 because we have a square base. And I have a formula right here to solve for y. So if I plug in 8 for x here and solve, then the height is 4 feet. So we got the dimensions of our aquarium. We want an 8 by 8 base with a height of 4. And that will be the least amount of surface area or least amount of material that will give us this volume of water. So there's some examples involving optimizing an open top box.